For as long as humanity has looked up at the night sky, we have wondered, what lies beyond the stars? What is the true scale of the universe? And how did it all begin? For centuries, these questions hovered just beyond our reach, whispered in the corridors of philosophy, woven into myths, and imagined in the pages of science fiction. Yet, it was only with the advent of powerful telescopes and technological marvels that we began to pierce the veil of the cosmos. And now, with the launch and deployment of the James Webb Space Telescope, that veil has been pulled back further than ever before. Humanity's most ambitious eye in the sky is showing us not just points of light, but a tapestry of time itself, revealing a universe far richer, more complex, and more astonishing than we had ever imagined. From its cold, precise perch far from Earth, the James Webb Space Telescope, or JWST as it is often called, began sending back its first major datasets. What it revealed immediately challenged everything we thought we knew. The universe, we realized, is not simply vast. It is teeming, intricate, and, in its earliest moments, far more evolved than our models had predicted. In one of its most ambitious observing programs, JWST produced a single colossal image, now known as the Cosmos Webb Field. This image, the largest and most detailed map of the cosmos ever created, stretches back 13.5 billion years, cataloging over 780,000 galaxies. Each of these galaxies, a universe of stars in its own right, now stands as evidence that the early universe was far from the quiet, primitive landscape we had imagined. The sheer number, scale, and maturity of these galaxies are forcing scientists to rethink fundamental theories of cosmic evolution. To appreciate the magnitude of what JWST has revealed, we must first recall the legacy of its predecessor, the Hubble Space Telescope. Hubble's ultra-deep field, captured in 2004, remains one of the most iconic glimpses of the distant universe ever achieved. For 11 painstaking days, Hubble stared at a seemingly empty patch of sky, revealing a celestial menagerie of roughly 10,000 galaxies, some dating back more than 13 billion years. Each speck of light was not a single star, but a galaxy containing billions of stars, planets, and cosmic mysteries of their own. From that single image, astronomers extrapolated that the observable universe contains roughly 2 trillion galaxies, a staggering number that dwarfs comprehension. Yet, even this remarkable achievement was limited. Hubble primarily observes invisible and ultraviolet light, and the universe's oldest light, stretched by cosmic expansion into the infrared, remained invisible to it. This is where JWST revolutionized everything. With its 6.5-meter golden mirror and state-of-the-art infrared instruments, it can see through clouds of cosmic dust that hid the earliest galaxies from previous telescopes. It captures the ancient light that has traveled across nearly the entire history of the universe, allowing us to see not merely snapshots of young galaxies, but the detailed structure, composition, and organization of the cosmos as it emerged from its infancy. The leap from Hubble to Webb is staggering. If Hubble's ultra-deep field were printed on a standard sheet of paper, JWST's Cosmos Webb Field, at equivalent resolution, would stretch into a mural over 13 feet on each side. It is, in essence, a complete recontextualization of our cosmic perspective, transforming a glimpse of a single city block into the sweeping panorama of an entire metropolitan expanse, with its neighborhoods, suburbs, and sprawling highways connecting everything together. The Cosmos Webb project was an extraordinary undertaking. Over 250 hours of observing time were dedicated to scanning a small patch of sky, roughly 3 times the area of the full moon. Thousands of exposures were meticulously stitched together, creating a single, seamless, contiguous image that reveals the universe's structure across vast epochs of time. The dataset is immense, cataloging hundreds of thousands of galaxies, each with its own story. This is not simply about adding more dots to a map. It is about revealing the underlying architecture of the cosmos. From the web-like filaments of clustered galaxies to the immense voids where almost no matter exists, JWST's observations allow astronomers to study the very skeleton of the universe, the cosmic web that has been forming for billions of years. As we explore this map, we are not merely looking at light, we are looking back in time. The nearest galaxies in the field show themselves as they were a few billion years ago, in their mature forms, sprawling spirals with elegant arms, massive elliptical galaxies in gravitational dances, and irregular galaxies in chaotic unions. In one particularly remarkable region, astronomers discovered an extraordinary object nicknamed the Infinity Galaxy. Two galaxies colliding in such a precise manner that they form a cosmic figure eight. Between these two galaxies, a supermassive black hole appears to be forming, not in the center of either galaxy, but in the space between them. This revelation hints at a previously unknown mechanism of black hole formation, one that could only be discovered when observing such a vast volume of the universe. Venturing further into the cosmos web field, we reach an epoch known as Cosmic Noon, roughly 10 billion years ago. This was the universe's most prolific period of star formation, a time when galaxies blazed with the light of countless young, hot stars. Even here, JWST has delivered surprises that challenge our long-held models. Astronomers have observed galaxies that have already ceased forming stars, quenched in a period when they should have been at their brightest, most productive. They have discovered remarkably structured spiral galaxies with well-defined arms only a few billion years after the Big Bang, an occurrence previously thought impossible. These observations imply that galactic evolution may have proceeded much faster than our models had predicted, forcing a re-evaluation of the processes that drive the growth, interaction, and maturation of galaxies. Finally, we arrive at the edge of understanding, the cosmic dawn, just a few hundred million years after the Big Bang. It is here that JWST's discoveries are truly paradigm-shattering. Before Webb, our best theoretical models suggested we would find very few luminous galaxies at this primordial epoch. Gravity, we believed, required more time to accumulate sufficient matter to ignite the first stars and assemble early galaxies. Yet Webb's images reveal a universe brimming with structure, complexity, and unexpected maturity. Bright galaxies appear in abundance, some containing heavier elements such as carbon and nitrogen, evidence that at least one generation of stars had already been born, lived, and died within the first few hundred million years of cosmic history. The record for the most distant known galaxy has been broken repeatedly. First, GDES Z14, observed as it existed just 290 million years after the Big Bang, and more recently, MOZ14, observed only 280 million years post-Big Bang. These are not the small, primitive proto-galaxies that textbooks predicted. They are fully luminous, structurally advanced systems, and they suggest a timeline that challenges the very foundations of cosmology. The implications are profound. If galaxies and supermassive black holes formed and evolved this quickly, it may require entirely new models to explain their emergence. The processes of galaxy formation, star formation, and black hole growth may have been more rapid, more efficient, or fundamentally different than previously imagined. Scientists are exploring theories ranging from direct collapse black holes, where massive clouds of gas bypass star formation entirely and collapse into enormous black holes, to new dynamics in the early universe that could accelerate galactic evolution. The very first chapters of cosmic history are being rewritten, and we are privileged to witness this reconstruction. Simultaneously, humanity has encountered another extraordinary cosmic visitor, an interstellar object passing through our solar system, designated 3I/Atlas. Detected on July 1st by the Atlas Telescope System, this object is the third known interstellar visitor ever observed, and it is astonishingly massive, roughly 7 miles across, comparable to the size of Manhattan. Traveling over 135,000 miles per hour, its hyperbolic trajectory confirms it is not bound by the sun's gravity. This is a one-way traveler, dropping in from the depths of another star system, swinging past the sun, and eventually retreating into interstellar space, never to return. Atlas functions not as a glamorous telescope, but as a planetary sentinel, scanning the entire night sky for anything in motion. When it flagged this dot,
astronomers quickly realized they were witnessing something extraordinary. Unlike typical comets or asteroids from our solar system, 3I/Atlas has a hyperbolic path and is a pristine relic of another star system. As it approaches the inner solar system, sunlight warms its ices, creating a glowing coma and potentially a magnificent tail, a display visible even to amateur observers. The James Webb Space Telescope has already scheduled observation time, aiming to examine its composition, using spectroscopy to determine the presence of molecules such as cyanide, diatomic carbon, and water vapor. These are the same ingredients believed to have seeded the early Earth with the building blocks of life. In a sense, this city-sized visitor is delivering a free sample of the material that forms stars, planets, and potentially life itself. While most data suggest 3I/Atlas behaves like a typical dirty